Hello there. This video is on AP Physics C Mechanics 2024 actual exam set 1 FRQ 1. So let's read this one out. All right, there is a block A and B of masses m and 3m. Okay, I can see that. Respectively, are arranged in a setup consisting of an ideal spring with a spring constant K and a horizontal surface. Okay, excellent. Friction between the surface and the blocks is negligible except in a region of the length d. So this is the length d in which there is a friction, otherwise it's frictionless. Where the coefficient of kinetic friction between A and the surface is mu, block B is attached to the string of length L. Okay, okay, all right. And a negligible mass shown in figure 1. Block A is held against a spring, compressing the spring to a distance of c, so xc. So we should notice that the spring has been compressed. Now at t equal to 0, the block A is located at the position x is equal to x naught, which makes sense, and is released from rest. After the block is released, the following occurs. At time t1, block A is at x equal to 1 after traveling a distance xc. At time t equal to t1, block A is at x1. So this is the mark t1. Let me take red color here. This is the mark t1. Let me, it's easy to track this way. After traveling distance xc, which makes sense because this was the xc. So when the block is released, it travels xc, and at t1, it reaches mark x1. Block A moves with the speed v, and the spring is at its equilibrium position. Okay, all right. So we are given that here the speed is v. I don't know if the speed v is to be taken as known or unknown, but I'm just marking all the information which we have. And the spring is at equilibrium position, which makes sense because it was compressed with xc and now it is at equilibrium position. Okay, no stretch. At T2 now, the left side of the block A is at x equal to x2. It means that the block is like this, right? And this is when T is equal to T2. Okay, excellent. After passing through a distance capital D across the region with non-negligible friction. Okay, all right, okay. At time t3, block A is at x equal to x3 and block A collides with and sticks to block B. So this is where the block A is coming now, M, and this is T is equal to T3 and it collides and sticks to the block B. All right, this is all just the information right now. The question is this. Now for parts A1 and A2, so this is A1 right now, express your answer in terms of mk, d, mu, and xc, and any physical constants as appropriate. Derive an expression for the speed of v of block A at time t equal to 1. Okay, pretty straightforward actually. Why is that straightforward? Because we just have to use energy conservation at this point, right? So I think I'm going to pull this information on the same slide, otherwise there will be a lot of uh, to and fro, which I do not want. Okay, all right. So what I'm going to do is I'm going to take this position as a reference. In fact, this position as a reference. So let me mark it as A, and let me mark this one as B. So I'm going to say that the total mechanical energy at A is equal to total mechanical energy at B, right? Because there is no friction. So the mechanical energy is conserved. Okay, guys, what is the mechanical energy? Mechanical energy is the sum of kinetic energy and spring potential and the gravitational potential. The good thing, the upside for this is everything is happening at the level ground, at least from A to B. In fact, from till this point, I know that height is not changing, so we can just ignore the gravity. Spring, of course, we have a spring of spring energy is given by half kx square. So it will be half kx sub c square plus, since the block is released from rest, there is no kinetic energy, so that's 0. At B, we know that they clearly state that the spring came at the equilibrium position, so there is no spring energy. Gravitational has already been ruled out, so I won't write that. But there's a kinetic energy of half mv square. So all we need to do is solve for v, right? Because that's what they want. They want v. So half k x sub c square is half mv square. Half and half is gone. flip the omelette here. So mv square will be equal to kxc square. Divide both sides with m, so it will be kxc square over m. And finally, if we take the square root on both the sides, it will be root of k x sub c square over m. And if you are okay with it, square root of x sub c square is just xc, right? So I'm just going to remove the square root from x sub c and remove the square root as well. Just to avoid confusion, I'm just going to rewrite this as x sub c square root k over m. So I hope this one makes sense. This was a pretty straightforward question, I think. Right. The next one talks about there an expression for the speed of VAB of the two block system immediately after the collision at time t3. Okay, so I'm just gonna pull up this information, this image once again. Once again, this question is based on energy conservation because uh, but be advised that there's a non-conservative force here, right? There is a friction over here, so you cannot really conserve the mechanical energy. So what we can do at this point is we can just find the velocity at T2. Why? Because the velocity at T2 of mass m is going to be same as the velocity of mass m at T3 because there is no friction over here, right? So because of inertia, it's gonna be at the speed at the same speed. So let's say that speed is v1 and this speed is also v1. Uh, um, if we know that the blocks stick together, right? That information was already given in the question. So at this point, what will I do? I'll conserve momentum, right? I will conserve the momentum. So conservation of momentum. What kind of collision is this, guys? This is perfectly inelastic. This is perfectly inelastic. This is perfectly inelastic collision. So since this is a perfectly inelastic collision, I'm going to say that the initial momentum, which is m times v1, I know that v1 is unknown, but I'm just setting up the equation first so that you know why I'm finding v1. mv1 will be equal to 4m. Why 4m? Because they stick together, guys. They stick together times some velocity v2, which they are interested in. In fact, they are representing that as VAB. So I'm going to do the same VAB. So these two are gone, m and m is gone. So I'm left with v1 over 4. In fact, v1 over 4 is VAB. Flip the omelette. So VAB will be equal to v1 over 4. And now I know that why I am interested in v1, because if we find v1, then a quarter of it is going to be the answer. Okay. Now the question is how to find v1, and I know that v1 and the v1 and at the speed at x2 is also v1. So I'm just interested in that. Okay, all right. I know that the energy which we had at this point, whatever energy we had at this point, the same energy we had at this point as well, because the mechanical energy is conserved, right? And since I know that my answer cannot involve the initial velocity, the velocity at x1, so I'm not even going to take the energy in terms of v. I'm just going to say that the energy at this position, which position? This position, and the energy at this position, that's what I'm going to compare, right? Because from here to here, the energy is still conserved, right? So it doesn't really matter if I take this energy or this energy. So I'm going to take the energy at A. I think we want A initially, right? Yeah, A. And let's say this is C. But please be advised, this is not mechanical energy. This is the total energy conservation. So I'm going to say that a work done by the non-conservative force, which is friction in this case, plus the total mechanical energy at A is going to be equal to total mechanical energy at C. Now, what is the mechanical energy at A? That was half kxc square. I'm running a little short on space here, so let me just add another slide. Okay. All right. Now, work done by the friction. Okay, let's write work done by the friction in a moment. first write a mechanical energy at A, which is half kxc square. Both the variables are allowed, so I don't have to worry about this. Mechanical energy at C will be half v1 square, and v1 is what we need to find. The only question is, what is the work done by the friction? And I know that the work done by the friction is just F dot D, right? In fact, work done by any force is F dot D. So that is friction force dot D. Dot means it's a dot product. It's not a simple mathematical product. It's a vector dot product. Um, Friction is obviously acting on the left side and the displacement is on the right side. So angle is 180. So we know that the dot product is given by FD cos theta. Theta is 180. So it will be FD cos 180 degrees, and the other things just remain as it is. Okay, let me continue my work over here. Once we are through with this, what do we have to do? Okay, F is something which we should know. And what is the friction force, guys? It's mu times normal reaction. Distance is capital D, that's given in the question, and cos 180 is -1. So there you go. There I have my minus sign, and this is plus 1 half kx sub c square is 1 half mv1 square. What is friction force? Sorry, what is the normal reaction? Obviously, the normal reaction is going to be mg because there is no other vertical force. So if I were to make an FBD, this is the normal reaction and this is mg. So Fn can be replaced with mg. And I think I have my answer, right? Capital D is allowed. Is that allowed? Yeah, it is allowed. We can use it in our answer. So excellent. I need to do is to have a little bit of math here. Let's multiply both sides with 2. So, and in fact, I'm going to write this one first because that's a positive term. So it will be kx sub c square minus 2 mu mgd is equal to mv1 square. Let's divide both sides with m. So it will be kx sub c square minus 2 mu mgd over m, and if you don't mind, I'm gonna take a square root on both the sides as well in the same step because this was v1 square, right? So this is going to be the gross expression for v1, and mind it, this is not our answer because our answer is, like I said earlier, we need to find a quarter. We need to find a quarter of this, right? We need to find a quarter of this because we were interested in what is the velocity VAB of the two block system. So all you need to do is take that gross number and divide by 2. I'm not really in a mood to write this again, so I'm just gonna copy this, come back. Oh my goodness, there is no space. So let me add another slide then. So VAB is gonna be 1/4 of this entire thing. So VAB is going to be 1/4 square root. If you want, you can distribute the m as well, or otherwise you can just leave it as it is. It doesn't really matter. You're going to get complete marks either way. So this is, I'm gonna box it up, and this is the final answer for B2. Hope this makes sense. There's more to it. On the following axis, sketch a graph of the kinetic energy of the block A as a function of time from t equal to 0 to t equal to 3. Interesting. Why is this interesting? Because it is interesting. That's because some part we have already discussed, right? Because we know that the kinetic energy of the block A is obviously going to increase because they are talking about the kinetic energy of the block. We know that here the entire mechanical energy has been converted into the kinetic energy, right? And as a function of time. So and we very well know that during this time its kinetic energy continuously decreases because there is a friction. And at this point, kinetic energy remains same. That is for sure. So I know that between T2 and T3 is going to be a flat line. It's not going to change because there is no force which can change the speed of the block M, correct? So that's what we have. Uh, okay, now guys, the first one is going to be interesting. Uh, If you're thinking that the kinetic energy is half mv square, which is absolutely correct, but then you are thinking that the velocity can just be written as v naught plus at, because as per, that's first equation of motion, v naught is 0 because it starts from rest. I can just square it, and acceleration is force over mass. Unfortunately, this is not applicable. Why is this not applicable? I'm talking about this duration from t naught or t equal to 0 to t1, because this equation is valid only when the acceleration is constant. Here the acceleration is not constant, it's continuously pushing, and as per the Hooke's law, the force is kx, and x is continuously increasing, so force is continuously increasing, so the acceleration is continuously increasing, so we cannot use this. So what can we use? Uh, uh, Either we can use integral calculus to derive this entire thing, or an easy way is to just use SHM. If you remember, in SHM, if we are, when it is completely compressed and we are releasing from this point where this is the equilibrium, then I know that the position is given by, A cos omega t. Why cos omega t? Because at t equal to 0, the amplitude is maximum. So it is starting from maximum, and that is the property of cosine, right? And if we now find the velocity, velocity is going to be minus a omega sine omega t. Why? Because the velocity is the derivative of the position function. So I just found the derivative of this. This we can right away use because A is constant. Omega, had it was performing SHM, would be constant because that's dependent on mass and K. Once again, omega. So it's only dependent on time now. So what will the kinetic energy look like? That's going to be half mv square, where v will be minus a omega sine omega t whole square. I don't really care about all this constants because I just have to graph it. So I'm just going to rewrite this as k times sine square omega t. I know that at t equal to 0, it is definitely 0. But what will the shape be like now? Because that's a sine square, right? So that's where your calculator will come in. Let me pull that graph for you. Okay, so the graph is going to look like this one, where you can clearly see that uh, the sine square is like there is a concavity change over here, and then it goes to maximum, and that's where we have to stop, right? Because this is where the velocity is going to be maximum because that's just getting released. The graph over here for the first section is going to look like this. Uh, next is this. Now you can use the equation of motion because the force is not changing, right? The force is friction, which is always constant. So I know that my velocity v at that point will be some velocity v, let's call it some velocity v2 at this point is going to be initial velocity minus acceleration times time. And the acceleration is constant. I don't really care what that is. It's just friction force over m, but I know that's a constant. So that's it. That's all what we need. So the kinetic energy is going to be half mv2 square, where v2 is v naught minus at whole square. What is this? This is a parabola, right? This is a parabola with x naught minus. So I think that's gonna be a parabola which is, I mean, if you're confused about this scenario, try to think about it in simple way. Like this looks like y is equal to x minus, sorry, y is equal to uh, h minus x naught or x whole square, because that's the x variable, which can also be written as x minus h whole square, essentially, because the minus is irrelevant over here. So since the leading coefficient is positive, that's going to be a graph which is opening up parabola, and opening up parabola, and obviously it's going to decrease. We know for a fact that that's going to be decreasing in nature. So it will tilt from here, it will tilt from here, and it will be a parabolic shape over here. So that's going to look something like this. It's going to look something like this. And at this point, it should go almost horizontal, because after that, as we already discussed, the velocity is not going to change. So the kinetic energy is also not going to change. So that's going to be a horizontal straight line that's going to represent that it is a constant. So this was a tricky one. But yeah, this is how we do this question. I hope that makes sense. Right, let's talk about the second question. Here we are talking about use principles of work and energy to justify the graph drawn in part B1 for the time interval 0 to T1 and explicitly reference features of the shape of the graph. So they are actually asking us to justified using the work and energy. So what we can say is initially, because we can justify two things. The first thing which we can justify is why is obviously the speed increasing, which kind of intuitive, but we can justify that. And why initially the curve was concave up, so the rate of change of kinetic energy is more, and then the curve is concave down, so the rate of change of kinetic energy is less. So we can say that initially, and we can maybe mark this point as some point which is not used. Let's call it T4. So we can say that initially from, so first of all, initially, F by the spring is maximum, right? Uh, Delta X is maximum. What is delta X? Delta X is the what do you call it as? The compression of the spring. From T naught to some point T4, which we have already marked. Now delta X is decreasing. In fact, we can just outline this as to justify that why is the speed decreasing. We know that the delta X is eventually decreasing because the spring is coming from its maximum compression to natural length. This would mean that the potential energy of the curve of the spring is decreasing. And since the mechanical energy is conserved, this would mean that the kinetic energy has to increase. It means that the velocity should also increase. So this justifies the fact that why is our curve continuously increasing in nature. So that justifies that the curve is continuously increasing in nature. Now we can talk about the concavity. So initially, now there's no need to talk about delta X. We can just say that initially the force of the spring is maximum. So obviously if the force is maximum from 0 to some point T4, it will make sense that the maximum force or the higher force will make the rate of change of uh, velocity or kinetic energy is positive. Why? Because the force is maximum, or it's between the maximum range. That's what we are trying to say. And from T4 to some point T1, the rate of change of the force is not maximum. The spring force has now decreased. The spring force has now decreased. So the spring force is now decreased, which would mean that the rate of change of velocity or the kinetic energy is going now negative. So it is still increasing. We justify that it is increasing, but the rate at which it is decreasing is less. That's why it tapers. It's concave down at this point and concave up at this point. That's how we can justify. Right. The next one which we have is the next part. After the collision, the two block system instantaneously comes to rest at time T4. Okay, they are using T4 here. That's fine. Which occurs when the spring makes a small angle theta max of the vertical as shown. For time t greater than T4, the system oscillates with the frequency of FL. The support holding the string is raised and the procedure is then repeated using a new string of length 2L. Okay. Indicate how the new frequency of the oscillation of the system 2L will compare to the old frequency. Uh, so don't you think this is more about the time period of the oscillation, which is given by 2 pi root L over G? And since the frequency is given by 1 over T, so the frequency is going to be 1 over 2 pi root G over L. So isn't that pretty evident that since force is inversely proportional to the square root of L, they're not even asking the factor, they're just asking which one is more. So if you increase the length, obviously the frequency is going to be decreased because it's inversely proportional to it. Uh, so which option are we going to mark? We are going to mark the this one because the new frequency is less than the old frequency because it's inversely proportional to the square root of the length. Okay. I think this is it for question number 1. Any questions, please post it down in the comment section. I'll see you soon with the next video. Till then, take care. Bye-bye.